Hi, my physics students. Welcome to another fun flip video with Mr. Bozade. Today we're going to look at how you can find the equivalent or effective resistance of a combo circuit. Right behind me, right here, we've got an example of a combo circuit. And up until this point, we know how to find the equivalent resistance of, like, say, a simple series circuit or a simple parallel circuit. In a series circuit, we know that the effective resistance is just all the resistors added up. And that makes sense because that'll make the total resistance increase when we add them up, which will make the current decrease. And we know if we add resistors in series, the current's going to get smaller. On the other hand, our equivalent resistance equation for resistors in parallel is 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. And that makes sense because as we add resistors in parallel, we would expect to get more current coming out of the battery, because the current not only will go down this branch, but it's going to go down the next branch and the next branch. And so more current, the battery will be pushing more current through the circuit as we add more branches. And that makes sense with our equation, because what this shows is that as we add more resistors, our total resistance is going to decrease. And if our total resistance or effective resistance of all this decreases, then that means the battery's going to produce more current. So things get a little bit more complicated when we have a combo circuit. Combo circuit is just a circuit that's a combination of series and parallel. And as you look at the circuit, you can clearly see that some of this circuit, some of the resistors are in series with each other, and some of the resistors are in parallel with each other. So here's my advice for condensing a circuit like this, a combo circuit, into one effective resistance, is to follow these steps. First of all, you look at your circuit and you're going to want to identify any resistors that are completely in parallel with each other or completely in series with each other. Then take those resistors, find their equivalent resistance, redraw your circuit, and then repeat until you're down to one single resistor. Okay, so let's give that a shot. So as I look at this circuit here, the combo circuit, what I see is I'm looking for resistors that are completely in series or completely in parallel with each other. Now, I've had students try to suggest that maybe, like, say, the 10 ohm and the 20 ohm are completely in series with each other. And my answer to them is that if I look at this and these two resistors, I don't know I could say they're completely in series with each other, because there's a branch or a junction in between them. And so I wouldn't say this is completely in series with that. I would say it's completely in series with this whole thing, but not just the 20 ohm resistor. Similarly, I've had students tell me that maybe the 20 and the 30 ohm resistors are completely in parallel with each other. And again, I would say not quite, because the 30 ohm resistor and the 40 ohm resistor are together in parallel with the 20 ohm resistor. So it's not that the 30 and the 20 are exclusively in parallel with each other, because that 41 is there too. But the 30 and the 40 ohm, those are exclusively in series with each other. So we can combine them. We know that those just add up to be 70 ohms of resistance. So we can redraw our circuit like this, where we've got our 10 ohm resistor, and it's in parallel with a 20 ohm resistor. And now that's in parallel with a 70 ohm resistor, like this, and we still get our 10 ohm, 20 ohm, and our 50 ohm resistors in those spots. So now we look at our steps. We found the Req of those two. We redrew our circuit and repeat. So we're not at a single resistor yet, so we're going to repeat. We look at this circuit and we want to try and identify any resistors that are completely in series or completely in parallel with each other. And my eyes go straight to the 20 and the 70 ohm resistor. Those are completely in parallel with each other. So we want to condense them or find their equivalent resistance. And we know that in parallel, the way we find equivalent resistance is we do our 1 over thing. So I'll redraw this circuit first. So here's my battery, here's my 10 ohm resistor, here's going to be the equivalent of those two combined, and then here's my 50 ohm resistor, like that. So 10 ohms, 50 ohms, and now I'm going to find what is the combination of those two. And so we know that the combination of the two, 1 over Req, the equivalent of those two, is equal to 1 over 20 plus 1 over 70 ohms. So I got to find a common denominator. So that's going to be 140. So that's equal to 7 over 140 plus 2 over 140. So we're looking at 1 over REQ is equal to 9 over 140, or really that's, so then we got to take the reciprocal of both sides, because this would be like the conductance, 1 over REQ, but we want to know what the resistance is. So we're going to take the reciprocal of both sides, and we find that the equivalent resistance of these two resistors is 140 over 9, which is 15.5 ohms. So the equivalent resistance of those two resistors in parallel is 15.5 ohms. So I can write this as 15.5 ohms. But we're still not at a single resistor yet. We're getting close. So we'll redraw this circuit again, and we can see now all of our resistors are in series with each other. So all we have to do is we have to add them up, and we find that we can redraw our circuit like this and make one resistor to represent all of those, and we find that that's going to be 75.5 ohms because we just add them up. 10 plus 15.5 plus 50 is 75.5. Now, so there we go. We found the resistance of one single resistor, of the whole circuit as though it was one single resistor. This battery here doesn't really know if it's connected to all of these or if it's just connected to one resistor of 75.5 ohms. What we could do next is if we knew the voltage of this battery to, like, say, be 15 volts, let's say that this battery was 15 volts, then we could use that information to find the current that is coming out of the battery. And we can do that, we can just apply our Ohm's law, V equals IR, V equals IR, and the voltage is 15 volts, which equals our unknown current coming through the battery, but our resistance is 75.5 ohms. And when we divide that over, when we divide 15 by 75.5, we find that our current is basically 0.2 amps. Well, what that means is because the battery could be hooked up to 75.5 ohms of resistance, or it could be hooked up to all these things the battery doesn't know. These are equivalent to each other. This battery is also going to be producing 0.2 amps of current. So this battery in this circuit is producing 0.2 amps of current, but this battery in this circuit is also producing 0.2 amps of current. Now we know when it reaches this junction here, because of Kirchhoff's junction rule, we know it's going to split up. Some of that 0.2 will go this way, some of the 0.2 will go that way. But it's going to come back together and combine at this junction, and it's going to be 0.2 amps again. So that 0.2 amps is going to flow through our 50 ohm resistor as well, 0.2 amps here and here. Well, we could quickly find the voltage that's dropped across this resistor and this resistor because, well, V equals IR. And so we can say, or the change in voltage equals current times resistance. So we can find that voltage drop. We can say the change in voltage is equal to 0.2 times 10. So that's going to be 2 volts. So 2 volts are dropped across that resistor. And we can do the same thing here. We can say that the change in voltage equal to 0.2 amps times this resistance, which is 50. So that's going to be 10 volts. So the change in voltage there is 10 volts. Well, now we can use our loop rule to find how much voltage is dropped across these two guys here. And we can find that if there's 2 volts dropped across this resistor and 10 volts dropped across that resistor, and if I make a loop like this around the whole thing, that means that 3 volts must be dropped across this resistor. So I can find the current here. We can say change in voltage or voltage drop equals current times resistance. The change in voltage is 3 volts. Current times 20 ohms. Divide 3 by 20 and you find it's about 0.15. So it turns out we've got 0.15 amps of current flowing through this branch right here. Well, we could do the same thing down here. There's a couple different ways we could solve for information down here. And what we could do is we could either Do the same thing where there's 3 volts across those two guys and they're 70 ohms. So we can do 3 volts divided by 70 to find their current. Or we know that the current was 0.2 and 0.15 amps of current flowed to this upper branch, which means in this lower branch, 0.05 amps is going to flow through there. And there you have it. What we did is we first took our combo circuit and we found 2 resistors that were exclusively in series with each other. We condensed them to 1. Found 2 resistors that were exclusively in parallel with each other, condensed them to 1. And then found all the resistors that were in series with each other and condensed them to 1. Then we found the current that was flowing through our battery. And because this battery and this battery are really hooked up to the same amount of total resistance, we knew the current flowing out of this battery is the same as that one. We knew that we could then find our voltages and our currents everywhere else using Ohm's law, the loop rule, and the junction rule, and we're able to solve for everything following those steps. Hope that was helpful. See you next time.